In this video, we are going to talk about chemical equilibrium and equilibrium constant. Let's say we have an hypothetical reaction A plus B goes to C plus D, such that the stoichiometric ratio, the stoichiometry of the reaction is A moles of A reacts with B moles of B to give C moles of C and D moles of D. And let's say that this reaction it occurs at equilibrium. It attains equilibrium. Now, when A plus B goes to C plus D, this reaction is known as the forward reaction, and this forward reaction will have a rate constant which we are going to call Kf, which is the rate constant for the forward reaction. And also, if we consider C plus D going back to A plus B, that is a backward reaction, and the rate constant for this backward reaction, we are going to call it K subscript B. So we can have two expression according to law of mass action for this hypothetical reaction. Remember that the law of mass action says that the rate of a reaction is directly proportional to the concentration of the reactant raised to the power of moles of the reactant. So we can say that for the forward reaction, we can say that the rate, let's call it rate of forward reaction, is equal to the rate constant Kf, then multiplied by the concentration of the reactant A raised to the power of the coefficient A, and then the concentration of reactant B raised to the power of coefficient B, according to the law of mass action. Also, the rate of the backward reaction, let's call it rate B, rate of backward reaction will be the rate constant of the backward reaction, K subscript B, multiplied by the concentration of the reactants here. If we are going backward as C and D, concentration of C raised to the power of the coefficient C multiplied by concentration of D raised to the power of the coefficient D. But then at equilibrium, when the reaction reaches equilibrium, it happens that at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. At equilibrium, the two rates are going to be equal to each other. So if the rate of forward reaction is equal to the rate of backward reaction, then we can say that Kf A raised to power A multiplied by concentration of B raised to power B is equal to the rate of backward reaction K subscript B multiplied by concentration of C raised to power C multiplied by concentration of D raised to power D. Okay, so now we can say that if we carry rate constant of backward reaction to the left hand side and we transfer these two to the right hand side, so we are going to have Kf over Kb is equal to C raised to power C concentration of D raised to power D all over concentration of A raised to power A concentration of B raised to power B. Now, the ratio of rate constant for forward reaction to rate constant of backward reaction is equivalent to the equilibrium constant K, capital K, which will now be equal to concentration of C raised to power C multiplied by concentration of D raised to power D all over concentration of A raised to power A multiplied by concentration of B raised to power B. This expression here is the general expression for equilibrium constant when considering concentration. So we can call this K equilibrium constant of concentration, Kc. So we can say where Kc is the equilibrium constant. So generally, if we go back to the equation, we can see that the equilibrium constant is the concentration of products raised to the power of mole of products divided by the concentration of reactant raised to the power of reactant. So generally, we can say the equilibrium constant Kc is equal to the concentration of products raised to the power of product all over the concentration of reactants raised to the power of the moles of reactant raised to the power of the moles of reactant. So now let's solve a question and see how to apply this equation. So let's consider this example. Write an expression for Kc for this reversible reaction at equilibrium. So we have 2 moles of NO, which is nitrogen 2 oxide plus oxygen gas gives nitrogen 4 oxide. How do we write the expression for Kc? Remember that the general formula is Kc is equal to the concentration of products raised to power the number of mole of products divided by the concentration of reactant raised to the power of mole of reactant. So here we can see that the product here is NO2. This is the product, NO2. So we put it in this parenthesis to represent the concentration. So we have the concentration of NO2. What is the number of mole? We have 2 moles raised to the power of 2. That is for the product. And at the reactant side, we have NO and O2. So we are going to have divided by the concentration of reactant NO, concentration of reactant NO raised to the power of moles of reactant, that's 2, multiplied by the concentration of the other reactant here is O2. What's the number of mole of O2 here is 1. That is why no number is written here. When there is no number written, then that is 1 mole. So we don't need to put raised to power 1. We can always leave it without putting 1. So this is the expression of Kc for this equation. Simple. So let's consider another example. Write an expression for Kc for this reversible reaction at equilibrium. Hydrofluoric acid plus water gives oxonium ion plus fluoride ion. So let's solve this. You can pause the video and try to solve this question before checking the solution. So let's solve this. We know that to write Kc, the general formula is Kc is equal to concentration of product raised to the power of mole of product over concentration of reactant raised to the power of mole of reactant. So here, what are the products? We have 2 products. We have H3O plus and F minus. So now we are going to have Concentration of H3O plus. The number of mole here is 1. That is why no number is written here. The number of mole is 1. So raised to power 1 is just the same as leaving it as it is without putting 1 here. So then multiply by the concentration of F minus, which is the other product, raised to the power of 1, because there's no number here, it's 1 mole, divided by the reactants. We have two reactants, HF and H2O. So divided by HF raised to the power of 1, and the other one is H2O, also raised to the power of 1. However, you have to notice something in this equation. H2O here is in liquid form. Whenever we are writing the equation for Kc, we only include substances in aqueous or gaseous states. We only include substances in aqueous or gaseous states. We don't include substances in solid, pure solid, or liquid states. We don't include substances in pure solid or liquid states. We only include substances in aqueous or gaseous phase while writing the equilibrium constant that depends on concentration. So here we can literally exclude this H2O from this equation, and then the equation is going to become Kc is equal to H3O plus multiplied by the concentration of F minus all over the concentration of HF. The reason why we don't include solid, pure solid, or pure liquid in writing the equilibrium equation is because we assume that the concentration of pure solid and pure liquid remain constant during the reaction. The concentration of pure solid and pure liquid remain constant during the reaction, so it is not affected by a shift in equilibrium position. So we generally exclude pure solid and pure liquid while writing the equation for equilibrium constant. We only include substances in aqueous or gaseous phase. So this is the correct expression for equilibrium constant for this particular reaction. All right. So let's consider this third example. The following equilibrium process has been studied at 230 degrees Celsius. 2NO plus O2 gives 2NO2. In one experiment, the reacting species at equilibrium are found to be NO is equal to 0.0542 molar, the concentration of O2 is equal to 0.127 molar, and concentration of NO2 is equal to 15.5 molar. Calculate the equilibrium constant of the reaction at this temperature. Alright, so how do we solve this? First of all, we have to write the expression for equilibrium constant for this reaction. But if you remember, we've written the expression in example 1, and if you can remember, we wrote the expression as Kc is equal to the concentration of the product, which is NO2, raised to the power of the number of mole 2, divided by the concentration of the reactant NO raised to the power of the mole, multiplied by the concentration of the other reactant O2 raised to the power 1. So now we are asked to find the equilibrium constant Kc, and we are given the value of the concentration of each of the species. So now we have the concentration of NO2 to be equal to 15.5. So we can say 15.5 molar, 15.5 raised to the power of 2, divided by the concentration of NO is 0.0542 molar. So we have 0.0542 raised to the power of 2 multiplied by the concentration of oxygen, 0.127 raised to the power 1. So we can solve this. So 15.5 raised to the power of 2 is equal to 240.25 divided by 0.0542 raised to the power of 2, which is equal to 2.938 times 10 raised to the power minus 3 multiplied by 0.127. So if we do this calculation, we're going to arrive at 6.44 times 10 raised to the power 5. 6.44 times 10 raised to the power 5. That is going to be the answer if you press your calculator well. All right. So you can try this exercise and drop your answer in the comment section. Carbonyl chloride, COCl2, also called phosgene, was used in World War I as a poisonous gas. The equilibrium concentration for the reaction between carbon monoxide and molecular chlorine to form carbonyl chloride is given below. At 74 degrees Celsius, our CO is equal to 1.2 times 10 raised to the power minus 2 molar, Cl2 0.054 molar, and COCl2 0.14 molar. Calculate the equilibrium constant. So I'm going to give you a hint. The hint is that you have to firstly write the expression for Kc, and then after writing the expression for Kc, you can go ahead and put in the values for the concentration of the reactants and the product. Then do your calculation and get the right answer. All the best. Don't forget to like this video, share the video, and drop your comment, drop your answer in the comment section. Don't also forget to subscribe to our channel, Chemist Explain. Goodbye. See you in the next video.